In this video, I would like to make the concept of integration very simple for you. It was invented by Sir Isaac Newton, so the credit goes to him. We have to understand why integration came about, why is it so important for us in real life, and does it have a relevance in real life at all? We need to understand that. So it all starts with a graph of y versus x. Both are variables. If we multiply y by x and if we get a third quantity which is useful, then integration makes sense. That multiplication needs to be done all along the graph of y versus x, and that becomes the area under the curve. If you take a wooden board and if you multiply the length by the width, we'll get the area of the wooden board. Let's look at the wooden board. On the left hand side, we have a simple rectangular wooden board on a graph of y versus x. It's a straight line graph. You take the height of the wooden board along y, multiply it by the width of the wooden board along x, and we get the area of the wooden board. But things get complicated on the right hand side graph, where the wooden board has a complex shape. How do we find the area of this? It's very difficult. So if we take three thin rectangles, and if we take the height of each rectangle, that will be along y, the width will be along x. Let's say it's a small delta x, and the area of a thin rectangle will be y into delta x. If we make many thin rectangles and add all of them up, a1 plus a2 plus a3 plus a4, we'll get a total sum or area, which will be the area of the wooden board. So if you look at the two graphs in front of us, on the left hand side, y is equal to fx is a straight line graph. On the right, y is equal to f of x is a very curved graph. The left hand side graph, as I explained earlier, is easy. Length into width and we'll get the area under the curve. The right hand side graph is not so easy to find the area under the curve. So here's where integration comes in useful to find it. And remember that the area under the curve has to be some quantity which is useful to us. It's not just for the sake of finding the area. We now take a real life physics example, that of a gas expanding in a cylinder with a piston. So the pink colored thing is the piston, which is moving from left to right, and the blue walls are the walls of the cylinder, and there is an entrapped gas between the piston and cylinder. The gas expands and does work. The left hand face of the piston is measured, and as the gas expands, piston moves to the right hand position, which is, let's say, a dead stop, and that face, left hand face of the piston, is also measured, and therefore we can get a graph of y versus x, and here it is p versus v. Pressure versus volume is the graph that is generated, and the red line shows that the pressure is constant as the volume increases. Therefore it's a isobaric process. If we multiply pressure by volume, that will give us the third parameter, which is the work done. Most important in physics, work done by the gas on the piston. So the whole purpose of integration is to get a simple way to arrive at this third quantity, irrespective of the complication of the graph that we have between two quantities. Here we look at the graph of p versus v, which is a hyperbolic curve, and we draw many thin rectangles from the initial position of the piston, which is A, to the final position of the piston, which is B. While the piston position is A and B, the real values of interest are the volume at A and the volume at B, the volume of the gas. The pressure versus volume is the red graph, which is clearly shown, and the rectangles are also clearly shown. So each small rectangle will have the area P into delta V. In this PV graph, which was a complex curve, the area under the curve also is complex. We can do this without knowing integration, but manually if we have to do, then we have to do three things. First, we have to divide the complex area into many rectangles as we saw in the sketch. Second, we have to find the area of each of the rectangles. Third, we have to find the sum of all the individual areas, A1 plus A2 plus A3 plus. Even if we do that manually without knowing integration, without knowing the equation of the graph, it will be first of all very painful, and secondly it will still not be very accurate. That's the problem. So to get an accurate value of the area under the curve, there is no option but to understand integration. Understand from this animation which I am showing you, where I started with very fat rectangles. When I say fat, I mean thick on the x-axis. Then I made them thinner and thinner. Then there was a gap and I had to add many more rectangles, which I have done. When I did all that, keep in mind the gaps that are there between the rectangles and the graph. You can see here that more the rectangles and the thinner they are, smaller are the gaps with respect to the graph. The smaller the gaps between the rectangle and the red curve, more accurate will be the area under the curve. For example, if we take this straight line graph and if we do an integration, proper integration, the work will be an integral of P dv from initial volume VA to the final volume VB, and P comes out of the integration because that's a constant, okay, in the integration, right? And the integral of dV is V, so that becomes P into VB minus VA. So it's very simple because this is a straight line graph. Things will become complicated if we were to look at the hyperbolic graph, which we will do now. Let's look at the more complicated graph of pressure versus volume. The initial volume here is V1, the final volume is V2, and the pressure decreases along the hyperbolic graph. Now, it's possible to see that if we were to calculate the area of each one of those rectangles, it would be extremely tedious, and still we will get a lot of errors, although the gaps look very small here. And the easier way would be to get hold of the relationship between P and V and then perform an integration using the formulae. So this graph is defined by the relationship PV to the power gamma is constant. So at any given point on this curve, you have P1 V1 to the power gamma, and at another point of the curve you have P2 V2 to the power gamma. They are all constant. With that, if you integrate this as work done integral of P into dV, you can see in the blue rectangle, from volume V1 to volume V2, we will get 1 by 1 minus gamma into P2 V2 minus P1 V1. P2 V2 is at the extremity of the curve and P1 V1 is the starting point. So this is a very simple equation to handle, and it will give us complete accuracy, and we are not worried about those gaps between the rectangles and the curve. That's the whole advantage of doing an integration. If we look at more generic examples, sometimes we come across y is equal to x square, or y is equal to sine theta, or cos theta, or cos squared theta. It's very clear that there must be a graph out there with that equation. So if we have to integrate y is equal to x square, there must be a graph of y is equal to x square, and therefore there will be some rectangles out there which we are not going to do, but which are there. So the advantage of integration is to find the area under that curve, and hopefully that area will be useful in practical real life. All we have to do is integrate y dx. You know that the width of each rectangle is dx and y is on the vertical axis. So for dx, integral of x square dx will be x cubed by 3, x to the power n plus 1 divided by n plus 1. This is a generic indefinite integral. If we have to do a definite integral, then let's say we have to do integral y dx from 1 to 10. It's given here and we will arrive at a number like 333. So in this way, we can see that the concept of integration is really very basic and simple, and we can also apply it to a real life situation. Thank you very much, and I hope you enjoyed this particular video.